Okay, let's resume. For the second module of today, we are going to talk about memory a little bit. And I'd like to start with an apology of sorts, because I was not entirely transparent with you when I say that functions are boxes, and what happens within the function stays within the function. There is a very important exception, and it's not time to introduce it. We are going to go through some concepts related to memory management, and I'm just going to try to give you a broad level overview of what is going on and not go into the details of why that is working in this or this way. But if at any point you feel like this is going too fast or not fast enough, let me know in the chat. So let's say we have a matrix called M, and it has zeros in it, and it's going to be integer values, and its size is 5 by 3, something like that. So that's our little matrix, right? And as we can see, when we call M, it's all zeros. It will be all zero. Yes, so M is all zeros. Let's now write a function that we are going to call f. And this function f will take a matrix M. So it's going to be an array of n64 for example. We don't really care. And with the m11 is going to be 1. So this function does nothing really interesting. It's well, I'm going to take an array as my input. It's going to be a 2-dimensional array that stores integer 64 values. And then I'm going to go in the first row, first column, and put the number 1. So let's call f on M. Oh, okay. I see. Let's call f, and let's run it, and it's telling us 1. So it's telling us it's 1, despite the fact that we have no return keyword in f, because by default the behavior is going to be return the last, the result of the last operation that was done. The last operation that was done is take 1, put it in this place, and so it's going to return 1. So let's look at M for a minute. Because something really important and really dangerous happened. And namely, M has changed. Because there used to be a 0 at the first row, the first column, but we have manipulated the value, we have manipulated this object, M, in the function f, and now the object M that exists outside of the function has also been modified. The reason for that is because you have two ways of giving an array to a function in computing. Either you do what is called passage by copy or passage by reference. Passage by copy is what R does. When you give a function written in R, you give it a matrix, it's going to work on a copy of the matrix that is different from the original object. The upside of that is that the original object is not modified. The downside of that is that it can be very slow because you need to create a new version of the object in memory. So if you have a very large matrix, let's say like 1,000,000 by 1,000,000, and that's like floating point, 64 numbers in there, you need to create that. You need to find a place for that in memory. You need to copy all of the values, and then you can start working on your function. Julia does passage by reference. So it's not copying the matrix, it's telling you, or it's telling itself. In fact, the matrix is located at this point in the memory in the computer, go work on that, but you are working on the original object. If you are doing operations that do not change the matrix, it's fine. If you want to do the sum of a matrix, it's not going to be changing the location, the matrix itself. So there is no reason to copy the entire matrix just to make an operation that will not change it. But that also means that you can change the content of your variable. So there is a little bit of convention here that I like, which is that every time you have a function that is going to change its object or mutate its object, if you want to be all fancy about it, we use an exclamation mark. So the function is not called f, it's called like f. Just beware, it's going to be changing the content of whatever you give it. That is not doing anything. It's not something that the computer do. It's something that people collectively agreed on and say, well, let's use this little sign to say there might be something might happen. This function has side effects. It is going to change the value that we have as an input. It's going to change at least one of its inputs. Which one is it going to change? Good question. You should be writing the documentation to explain which one is going to change and how and document everything. But whenever you see a function with an exclamation mark at the end, it means that the person who wrote this function was explicitly wants to let you know that this function is going to change its argument. When you're writing your own function, you can write things that change the argument without putting an exclamation mark, because then again, it's not something that does anything technically. It's something that is a writing convention. It's part of the style of the language. But it's a good idea to always adhere to this convention because it's a good information. So we are going to rename this function here, like recreate this new function f. One thing that is interesting, just to let you know that it's really two different functions, is that when we create f exclamation mark, it's a generic function with one method. It's not a new method of f, it is something that is different. So let me show you how we can do that. So let's say that we want to have a function that is going to be changing its argument and a function that is not. So we are going to do a function f of that thing. And we would like it to behave in the way that function in R would behave. Like it's going to be changing something, but it's going to change something that is not the original object. Well, what we can do is do something called k and explicitly say, make a copy of the input. And when you have made a copy of the input, call f on the copy of the input. So this one is going to be change the input, and this one is going to be copy the input and change the copy. They're not two methods. I want to emphasize that. They're not two methods of the same function. They are one method of different functions, but it's just a convention that exclamation mark is going to be changing, I think. So let's try again. We're going to make a matrix called n, and it's going to have zeros in 64, 3, 3. If we call f of n, the result is 1. That's an interesting thing. It's not returning the entire matrix. Why? The reason why is that because the last operation we do is f exclamation mark of k, and the result of x exclamation mark of k is to put 1, and so it's returning 1. And so also by convention, it is generally recommended that the function that have an exclamation mark in the end return their arguments. So let's see if that fixes it. We have f n equals 0 in 64 of size 3, 3, and we call f, and it is going to return a matrix that has a 1 at the first position. Now, if we look at n, we can see that n has not changed, right? Because when we call this function f, the first thing we do is a copy, and then we modify the copy, and so the original object is left unchanged. But if we want to change n, we can. We just use f exclamation mark of n, and no n has changed. So that is something that's very interesting and very that comes up very often. In some cases, you want to change the input. In some cases, you don't. And the sort of design pattern that we would use in this case is we're going to define two versions of the function. One that is changing the input, and a second that is creating a copy and then changing the copy. So it looks like you have, so the function that changes the input is the one where most of the action happens. And then the other one is usually often just create a copy and then call the actual function on that. But what that gives you, this little extra function here, it gives you the opportunity to decide if you want to change the input or if you want to return a new object with the change in it. Again, that is something that I understand can take some time to figure out, and so it's a good idea to play with it and experiment a little bit. One of the things that I'd like to show you is that this can have some important consequences in terms of the performance of your program. So let's call O. We'll do 0 in 64 to 5. Why not? Okay. Let's look at the time it takes to do f of n. Well, it's pretty fast. Okay, I should have been a little bit more ambitious. Okay, so when we do f of n, I'm just going to add a semicolon at the end of the line so there's no input, only the output of time. When we call f of n, it takes 0.0002 seconds, whatever, and there is one allocation, which means that we're taking something from the memory and putting it in another place in the memory. That's one allocation. When we do f of n, there is no allocation. We're not taking things from memory and putting it somewhere else. So now the object we're using is very small. It is the size of an integer 64 times 9. And so that is not something that is going to be taking a lot of time to copy. But if you have a larger matrix, let's say you have a landscape of 500 by 500 and it is storing floating point value who are all different. So there's no shortcut that you can take. Or it might take some more time to copy. And so the difference in terms of performance is often going to come down to the fact that either you need to move objects in memory or you don't. And when you don't need to take things, create a new version of them, find a spot for them in the memory of your computer, and then perform the operation, it's often better not to do that, because that is a place where performance costs can be very strong, very severe. And so that's one of the mechanisms that we have is we can either copy the argument and modify it, or we can not copy the argument and work directly on it. That has a very important consequence, which is that when you are writing a function that is manipulating an array, there is a risk of changing your input in a way that you don't necessarily anticipate. So you need to be careful that you're not changing the input of your function. But that's also something that you can use to your advantage, right? Because if you have if you want to do a simulation of a landscape over time, for example, and you have a grid, you don't need to, if you want to do 10,000 time points and you don't want to keep all of the 10,000 times points, you're interested in what happens in the end, you don't need to define 10,000 landscapes. You can define only one or two, maybe, depending on what you're doing, and then you just modify them in place. So instead of having to allocate 10,000 times 500 times 500 spots in your memory, you just need to do it once, and it's going to be a lot faster because it's going to be what's called in place. We know where things are, and we modify the things where they are instead of creating a new copy and finding a position for them. So that's something that is potentially, it can lead to dangerous consequences where you change your objects without realizing that you are changing your objects, which is very bad. But it's also a really interesting mechanism in terms of efficiency because you are changing things in place. And so that you can have code that goes very fast. And you can have code that goes very fast, but also code that goes very wrong. And so the question is, how do we, there are some mechanisms we can use to make sure that that the code that we're working is working in the way that we actually want it to work. And the answer is, of course, yes. So let's do, let's maybe create a new file, I would say. Yeah. Let's create a new file, which we're going to call module 1 class 3 testing dot okay, I'll get it .gl. Okay, so testing. Yeah. One thing that I've mentioned at the beginning of the class is I like it when a code goes wrong and it gives an error message because we know something is not working. What I don't like is when a code is running up until the end and gives you a result, but the result is wrong. Because when you're using this programming for science, if you have a result that is wrong, then you are doing science that is wrong. And that is not an optimal situation for anyone to be in. So let's try to think about ways we can ensure that the code that we run is right. There's no magical solution. It's not going to be, I'm not going to give you a function which is called like make it right, and you give it your code and it's going to make it right. But what we can do is think about practices that are going to decrease the chance of us making mistakes. We've seen a few of them, actually. We've looked at documentation. We've looked at comments. We have looked at using the dispatch system to make sure that we run the correct method and the correct input. We have looked at annotating the return type of function to make sure that the function are only going to return things that are of the correct type. These are all mechanisms that are helping with the fact that we run things in the condition that we want them to run. But we can do more than that. So let's write a function with a bug. Let's call a function called moyenne. And it's going to be taking a n, which is a vector t, where t is going to be a number. And we're going to write a function called moyenne that has a bug in it. So let's think of a way to make this wrong. Well, we know that the actual way to calculate the average would be we take the sum and we divide by the length. And let's say, okay, we're going to create a variable called sum, and it's going to be initially 0 of t. We know what to do with that. And then we're going to make an iteration. And it looks like for I in, and let's say like we're distracted by something. You know, you like pretending that you're programming, but you're actually watching Netflix in the background, and you hit the wrong key. And instead of typing 1, you type 2. We're gonna do sum plus equals n of I. Okay. Let's do something even better. Let's say you try to access your array. And so you look at what is an n of 1, and then you copied and pasted this code that happened surprisingly, depressingly often to me. So I'm just judging myself here, we just add the same element over and over again, something like that. So this, and then we return the sum divided by the length of n. Okay. That's a good example of a function that, if you look at it, superficially, it looks okay. We create a variable that has 0 in it. We are making a loop through the entire values of n, and we are adding the values to this loop. Only we've made 2 mistakes. The first is we are not iterating on the correct number of things. And the second is, even if we were iterating on the correct number of things, we are adding the wrong value to the sum. And so the results are going to be all wrong. So let's say, okay, we have defined this function, and now we have a series of values. Let's not use value, which is a function. Let's use v. And it's going to be 1, 1, 2, 5, 4, 3. Okay, something like that. And we want the average of that, so moyenne of v. Going to tell us, 0.83334. That's okay. And like, yeah, that checks out, I guess, because we don't really think about what an average is. It's like, okay, that's like the average of 1.12543 is 0.8, whatever. And then we move on with our lives, and then we build results on top of that, and they are wrong. So the question is, how do we avoid this situation? It's not a matter of using the correct dispatch or documentation or commenting. It's a matter of the code is doing the wrong things silently. So there is a package which is called test. I don't actually think we need to add it. It is part of the standard library. Let's use it. Using tests. No, okay. So the general idea is that when we're doing something, we should get a good expectation of what the result will be in some specific situations, right? And so we are going to do that. So using test, and it comes to the macro called test. And we could do things like, okay, let's have a look at how it's working. We can do test 2 equal 2. And that's going to tell us test passed. Let's check that 2 equal 3. It's going to tell us test failed. It's also going to tell us where, and so on and so forth. Okay. And when it fails, it's going to tell us the expression 2 equal 3 has failed, and there was an error during testing, and so there's something that's not quite right with what you're doing. So let's make a test of our moyenne function, right? We say like the moyenne of 2 and 2 should be 2, right? It should actually be 2.0 because we're going to be dividing anyway. And so that's interesting because we have the first error here. You say, well, you wanted the average of 2 and 2, and it's supposed to be 2 according to what you put in the test. And of course, that's making the assumption that the test itself is right, which is not necessarily the case. But the evaluation, the result I got when I was running the code is that the instruction moyenne of 2 and 2 is actually 1. So your function is not working. Function is wrong. And that's sort of telling you, well, there is something that doesn't work here. So we can get back here and fix our function. It's okay, like I'm not iterating on the correct number of things. Let's fix that and run the test. And if we run the new test, so I'm just going to, so what I'm going to do, so you can see the progression here, is I am going to run that chronologically. So let's fix it. So let's fix number 1. Yeah. And then let's test this function. Let's make sure that we have this one. Okay, so fantastic. The test is working. We have fixed our function. So now that we have fixed our function, we can get back to getting the average of our values of series of values here. And I say, okay, so the average of 1, 1, whatever was in V, 1, 1, 2, 5, 4, 3 is 1. That also doesn't sound right. And that's weird because we wrote a test and the test is passing, but the function is still not working. And the reason is that we have tested a behavior that is not really, that is also a behavior that we have, that is a, that is covered by another bug. So Zach said, I'm not able to add the package test. I don't think you need to add the package test. You could do, it's part of the standard library, so you should be able to do using test, and then it's going to be loaded for you. So the specific bug that we have here on row 26 is that we are only adding the first value. So we're adding value 1, and then instead of having a value 2, we're also adding value 1. But during our test, we have tested with a number that only has the same value. And so it doesn't matter if we're adding the first or if we're adding the correct thing, because our test is not really well written. So we're going to keep this test here, and we're going to add a new test, which is the average of 2 and 4 should be 3. So the first test is passing. The second test is not, because now it's taking the first number and then adding the first number again instead of adding the second number. So I'm like, okay, the function is still wrong, and we can go and fix the function again. And we read it very carefully, and we say, okay, I see, this should be n plus y. Okay. So we can restart this function, and then we can run both tests, and both tests are passing. And now if we run the average of V, that should give us something that is 2.6, and that checks out. I don't know what the actual average of this number is, but I can tell you that it's probably that. So tests can do a lot of things. I'm going to see one or two more of them, but it's very important to understand that you have this thing. You're able to use these things when you are developing your own functions, because the function originally was working without throwing any error, but it was doing the wrong thing. And then we wrote one test, and this test, it was working, but it was working because it was also affected by a very specific bug in the function. And so we had to write a second test that was also capturing the other bug and let us identify what is going on. So that is a second big area of good practices, and it's actually it's actually far more complex than that when you want to perform an actual test of an entire package, for example. But designing tests means that you need to come up with expectation for the behavior of your function, and you need to come up with situation for which you can predict the output, and you need to check that what you have written is going to be conforming to these expectations. That also, and let's get back to probably 2 weeks ago, I think. If you write functions that are small, they are easier to test. Our function for the average here, it's only 4 lines, and so it's not doing a lot of things, and so we can test it with like 4, 5, 10 well-specified tests. If you have a function that is hundreds of lines of code, you need to write a lot of tests to make sure that it works. But if you have a very small function, and each function can be tested a lot more in depth. So that's always a good approach to try to write a function that is as small as possible and then make sure that it works. Test has quite a lot of different macros, right? So there are a lot of things, like you can test that there is no warning that is thrown. You can test that there is a warning that is thrown. You can test that there is a specific type of error message. When you are writing packages that are more complex, you want to have some ways to check that some condition are met and then throw an error message or not, and test can do that, right? So that's a thing that you can you can do. There's a good documentation of the test module that you can have a look at. But it's always a good idea when you're doing something, you want to make sure that it works, think of a test, and then write this test, and then make sure that it's working. It's also very useful when you want to change the behavior of the code of a function. Well, let's say, for example, we say, well, I'm taking something here, which is sum, and then I'm adding every element in here. I might as well say, well, let's do the sum of n. We have changed the content of the function. We want to make sure that the change of the content of the function is not going to be creating new issues. So you change the body of the function, what it does, not what it does, how it does it, and then you run the test again, and they're still passing. But if we had introduced a change here that was breaking, that was not right, you would have made one of the tests hopefully fail. So in the previous module, we've discussed the fact that writing code it's about writing code, but it's also about writing a lot of comments and documentation, and that's one thing. But then making sure that the code works is also about writing a lot of tests, and the tests, in a sense, are also documenting the behavior of the function in a way the computer can understand. And so the result of that is writing the actual code is going to be taking not a long time compared to writing the documentation, writing the comments, and then coming up with a thorough suite of tests that you can use to ensure that the code is actually working. And that's something that is maybe a little bit surprising, but most of your time is not going to be spent working on the code. It's going to be spent working on what is outside of it, because you want it to be usable, you want it to be as transparent as possible, and you also want it to be trustworthy. You want the code to be working well. So that's all sort of practices that you can use. We're just scratching the surface, especially of testing. It's something that takes a lot of practice to develop. There are ways to automate the testing. It's something that is an area of study in and of itself, but we can come up within the context of this class with very short tests of a function to make sure that they're doing the thing that we want. So that is something that I wanted to mention with you. There's another important macro that is somewhat related to testing, which is called assert. And the assert macro is something you could sprinkle into your function, I would say. And what it does is, if the condition is true, it does nothing. But if the condition is false, it's going to give you an assertion error. So that works and that doesn't. It's not the same as testing. It's not something that you would do externally to the function. But if you know that two values should be equal, or that a vector should have a specific length at some point in your function, then you would be justified in using assert. And then if this condition is not met, your function is going to stop. It's going to crash. It's going to say, it should be true. It's not. I'm not going to go any further than that. Fix the issue in the data, or fix the issue in the function. The sort of rule of thumb, that's again not a technical restriction. It is a convention within the community, is to use assert when we are 99% sure that the condition is going to be met. So you're going through the instruction in your function, and you say, like, there's almost no chance that this condition is not met, but I'm going to put assert, because if the condition is not met, something very wrong is happening and I want to catch it. So it's not something that you should use to do like all of your testing, or if the parameter in the right sort of value or something like that. It's just an internal test, and if the assertion is wrong, something really, really bad is going on that you need to figure out. What else? Oh, let's do a quick example. Let's say we want to let's say we want to calculate the let's say we want to calculate the average, but we only want to calculate the average when the series of values has more than 4 elements in it, right? So we could do assert length of n is larger or equal to 4. That's a thing we can do. And then we could call this function with 1, 2, 3. And it's going to give us an assertion error. So in a sense, it's correct behavior, right? We say, well, if the condition is not met, I want this function to crash. And then the function indeed does crash because the behavior is condition is not met. That's a correct behavior, but it's expressed in a wrong way, because we have a far more powerful way of doing sort of things that is actually telling you something about what is going wrong. So we're going to rewrite this function. Instead of using assert, we are going to do if n is smaller than 4, we're going to throw. So throw means that we are going to literally throw at the user's face an error message, and it's going to stop. The function is going to stop here. And there are dozens of different type of error messages, but we're going to throw an argument error here. And it says length of n should be at least 4. 4, okay. So the advantage of writing the function this way is that if we do that, it's going to oh yeah, sorry. Again, little bug. You can see how easy it is to make a mistake. So if the length of n is lower than 4, so instead of having an assertion error, let's say n is the length of n is not larger or equal to 4. What we have is an argument error with the text that we specified. And so it's saying, well, the length of n should be at least 4. And that is also sort of a dialogue that you are having with your user, where you say, my function is expecting a very specific condition to be met, and I'm telling you your argument, which is n, it should have this value. We can make that even better. And that is why error messages is so important. It was like the length of n. Let me try that. I haven't really experimented with that yet, but it should work. Should be at least 4, and say you passed n equal. Remember that we have string interpolation, so we could be a little bit crafty, which has length of n. I don't know if that's going to work, especially the 3 quotation marks, but let's do that. Yeah, okay. So what we have here is a more complex error message, which is telling what the error is, and then what specifically is the value that we used, and then what is the length of this value. So in terms of understanding why the program is not working, right, it's a lot easier. It has a lot more information for the user. When you're saying, well, instead of saying there was an assertion and the assertion was wrong, it's like, okay, there's something that's not obviously not working, but I don't know what it is. We have written a specific message that say, well, the error has to do with the argument. And then we write a little bit of text. It's also a form of documentation. We're documenting the thing that the user is doing wrong. And obviously, the fact that n should be at least 4, well, it must be in the documentation of the function as well. But when we're running the function with the wrong argument, it is stopping, and it's explaining why it's stopping, and then giving some ideas to what to fix. And the importance of good error messages should not be underestimated. Just because they can that can mean the difference between a fix that is going to be taking you 5 seconds and a fix that is going to be taking you 5 hours. Just to give you an example, I was using a package where I was trying to read a CSV file or something like that, and the error I got was invalid file, something like that. And I was like opening the file in Excel and then in LibreOffice and importing it into Google Doc, and it was a perfectly valid CSV file. And I spent a lot of time just like converting everything, working on the CSV file, trying to remove some columns, whatever. And then I actually looked at the code of the package, and what they meant by invalid file is the file does not exist. And I spent an incredible amount of time trying to figure out what was wrong with the file, because the package told me it's invalid. And it was not invalid, it was just not here. It was not here because I forgot a semicolon, an underscore in the path at some point. But so in terms of being friendly to your user, and the user is often going to be yourself, having an error that is not ambiguous and explain what is going wrong and maybe give some ideas about how to fix it is going to be saving you a lot of time. And what you want is the function to stop as soon as possible if something is not right. And again, that's also an illustration of the fact that, look, our function is doing two things. It's doing these two things, but in order to make these two things safely, we have added a number of lines of code here. And so the actual, the more we work using good practices, the more code we write that is not about the actual calculation. It's about making sure that the calculation is not going to be wrong in the end. That's what we care about very, very dearly. And that is why documentation, commenting, testing, dispatch, checking the return type, but also throwing the correct error messages is so important. So that wraps up the actual introduction to Julia as a language for this class. We are going to break for another 15 minutes, and then we're going to do some plots. We're going to look at making figures and changing colors, making legends. It's all going to be very light and pretty and not complicated at all, which is going to be a nice change of pace. But just remember that when you will be writing your assignments, I'm expecting to see some function, and I'm not expecting to have them thoroughly tested or to have a long series of possible error messages that capture everything that can go wrong. But I'd like to see comments. I want to see a documentation. And if there are things that are obvious, things that should be caught by an assertion, I would like to see this assertion. So I'm not expecting you to follow all of the best practices immediately. That's not the point. But I'm sort of expecting that you will be building these best practices into your work as the session progresses. So I will see you in 15 minutes, and we will be talking about figures.